One, two, three, A and P. Let's talk about the cardiovascular system, finishing off with the circulation. Remember, we have heart, blood, and the circulation. All three of these elements are working together. Here we've got an awesome plastinated hand here. That's a type of preservation that's popular in the Body Worlds exhibits, etc. And everything that you see depicted in red, those are blood vessels. You've got arteries, and in smaller arteries, we would call arterioles, all the way down to the capillary level. And you can see that we have congregations of these capillaries, for instance, at the fingers. What would that allow us to do? Well, we've got the far reaches of our extremities, our fingers and our toes. We need to have nourishment there. Also, our sense of touch, the sensory nerve endings that live down there, they need nerves, require blood as well. So the sense of touch, pain and temperature, the intricate muscles that are attaching to our digits and hand and wrist and forearm, all those structures need a blood supply. And so here you have that occurring. You also see how there's large blood vessels that feed to the one side, and then on the other side we've got circulation that comes the other way. So there's all kinds of overlap and interplay between these blood vessels trying to service various parts of the anatomy, the circulatory system. Let's talk about what the blood vessels look like, and then how we can influence the flow of blood, how we can influence blood pressure, and then a little bit about capillary exchange. So there's all kinds of things that circulate, as I stated in our lab in person. We've got money circulates, magazines circulate, the meteorology, winds, currents, temperatures circulate. They ebb and they flow. Farts circulate. Almost everything flows and circulates. In particular, fluids. So we're talking about blood, that life-giving substance that is a connective tissue. How do we connect it between and distribute it among our various anatomical parts? The circulation. So here's a circulation. We've got an artery, illustration of some blood fluctuations in blood flow here. Up above, we've got normal blood vessel, and then down below, we've got a narrowed blood vessel. We could also call this dilated or constricted blood flow. So if we needed blood to an area, the circulation has the ability via the autonomic nervous system to influence the blood flow. If we need to service a particular area, maybe we would dilate those blood vessels, thereby making them wider. Their diameter would increase and their flow would increase. If we need to increase the blood pressure, well, what would we do? We've got a garden hose, we stick our thumb on the end of it, and that pressure that occurs is going to cause the blood to flow more quickly to a particular area. I also use the analogy of riding on I-76. Let's say you go from 2 lanes, and then for some reason there's a obstruction or a car accident or something, and it all goes down to 1 lane. What does that do? There's all kinds of people backed up in front of that or prior to that blockage, and that is going to cause an increase in pressure and traffic and flow of cars. So, circulation. We've got arteries, we've got veins, we've got capillaries, we've got different gauges of pathways of blood flow. We know that arteries are typically depicted as red and veins are depicted as blue. And even in our cats that we're dissecting, we have tagged the vasculature accordingly. So you can see the veins and arteries, and they're artificially colored. Okay, so here's some arteries and veins and capillaries. We're all working together. They're all in proximity. Once again, they're just different thicknesses of blood vessel. The diameter of the lumen or the hole that is created by the blood vessels, they're different sizes to serve different areas. I talked previously, you got arteries, and there's elastic arteries, large diameter arteries like the aorta. And then there's medium-sized arteries, which are going to be medium in size. And then finally, we've got arterioles, which are the small arteries, still have elastic and the ability to dilate and constrict. And then finally, we get down to the capillary level. And if you see in the center here that you see some lipocytes or fat cells, and intermingling in there, we've got arteries and veins coming together and exchanging fluids, tissues, blood products. And so that is called an anastomosis, where arteries and veins kind of meet. The pathway of blood flow, we know it. We can trace the drop of blood through the heart from the right atrium, venous return to the right atrium, all the way through to the systemic circulation, right? You know how to do that now. We can see that there's arteries and veins playing various roles in order to service the anatomy. Blood vessel structure. All right, so what does an artery look like if we histologically regard the blood vessels? We know that there are 3 different levels that we can study. So we cut these vessels in half in a horizontal section, and we look at them. What does it look like? Well, the inside, we've got something called the tunica interna, or the tunica intima. This maintains intimate contact with blood cells, the formed elements and plasma, as they flow down this log flume, right? That's the tunica intima. And this is lined with a single, simple squamous epithelium and a little bit of connective tissue, and very, very slippy, so that blood cells can flow. The tunica media, when I say media, you should think, excuse me, muscle. So the middle aspect of any artery is going to have this smooth muscle layer, which allows it, under the control of the autonomic nervous system, to dilate and constrict. This is what allows us to change the diameter of the blood vessels. Finally, the outside, or the tunica externa, otherwise known as the tunica adventitia, this is kind of like a connective tissue sheath. Think of like the outside of a garden hose that helps us maintain the integrity of the hose itself. So 3 layers, and that's what they do. We can see an artery here, which is a muscular artery capable of dilating and constricting. We've got a nice round lumen in the center. And then adjacent to that is a floppy vein. You see that the vein doesn't have as much integrity, so it's kind of a passive source of flow. Once again, muscular action and veins that possess valves, allow the blood to flow back to the heart, ultimately dumping into the right atrium via the superior and inferior vena cava. Here's an elaboration on the various parts of the wall of the blood vessel. Tunica externa, or adventitia, the outside. Tunica media is the middle, smooth muscle. Tunica intima, slippy and slidey. It's comprised of what's called endothelium, which is a single layer of squamous epithelium. Different gauges of arteries and veins. So here we can see them in the image to the right. We've got arteries that are called conducting arteries. They're the largest. We're talking about the aorta, all right, is a great example of that. It's about the thickness of your thumb. It's the largest, in-chargest artery in the body. It rules the systemic circulation. Distributing arteries are muscular arteries. They've got a very prominent tunica media because they can dilate and constrict under the control of the sympathetic and parasympathetic nervous systems, the autonomic nervous system. And these distributing arteries are basically going to stem from the aorta, and they're going to branch off and service different parts of the anatomy. Maybe the intestines, maybe the kidneys, maybe the heart and lungs. Finally, the resistance arteries are small, and you might call these arterioles. They're going to be like the terminal branches that are going to plug into the various types of A&P there. And so their dilation and constriction is going to allow us to service the all of the anatomy. All right. And once the resistance arteries, where they end, the capillaries pick up. Capillaries are one cell thick. By that I mean that if you have red blood cells in a capillary, they're stacked in there like dimes or like pennies, whatever the hell you want to think of them as, one behind the other. That's about all can fit in the capillaries. And so here they are, the terminal branches. If you think of this as a tree, we've got to the left of the image, we've got those large diameter arteries, and then the medium muscular arteries are going to branch off, and then find the little terminal branches, little tiny branches will be arterioles, and finally capillaries. And those capillaries are one cell thick, and they're going to be responsible for creating these capillary beds that are going to allow nutrients and oxygen and waste products and all that stuff to be exchanged. Capillaries are extremely important. Okay, if you're somebody who takes good care of yourself, you got a healthy subject, the capillaries are going to be rich. You can take your finger and you can press on the person's fingernail, your own, do a test called capillary refill. You will blanch the finger, so otherwise pushing all the blood out of the digit, and then it'll return really quickly. The rate at which it returns is going to indicate a degree of perfusion, or how fast is the capillary refill. So there are different types of capillaries. There are continuous capillaries, which are basically one tube, like a straw, and then you've got these things called fenestrated capillaries, which have holes, or these little dashes throughout, so that particles can come and go from that straw, like a straw with holes in it. We're going to talk in a bit about the importance of those fenestrations. They're key. Here we've got electron microscopic image. We've got large, probably arterioles, and then we're branching all the way down to the capillary level, and see that everything gets very, very small, and all these intertwined branches of capillaries, like a ball of yarn in the background there. And these capillaries, the flow to the capillaries is extremely important. There's something that you're going to see here. It's called a precapillary sphincter. That will essentially act like a spigot for your garden hose. If you want to turn on the flow, these precapillary sphincter will either open or close the flow to that particular area. And this is one big way, one important method of, let's say, responding to temperature. So you go outside, you have normal perfusion, normal blood flow throughout your body, pretty uniform. You're in room temperature, and then I just busted ass there. Excuse me. Now, if you go out, step out in the freezing cold, these precapillary sphincters are going to shut off the spigot, and there's not going to be any blood flow or less blood flow to the extremities. People with Raynaud's phenomenon or Raynaud's syndrome, if they go out into the cold or they endure some stress, their entire hand or fingers might go completely white because the capillary beds, all the flow has been turned off of blood to the capillary beds. And it is, you see, a function of the autonomic nervous system, because the autonomic nervous fibers are plugging into the precapillary sphincter, and they can turn it on or turn it off. Arteries and veins. So here we've got an artery on the left with its 3 layers, and then we've got a vein on the right with its 3 layers, but less functional in terms of dilation and constriction. And then in the far beyond there, we can see that there's an intermingling of the artery and the veins, the flow of which, and that is called an anastomosis, as mentioned previously. You notice there's a feature in veins that is a valve. You see this right in the center of the vein there. There's a valve, and we've talked about that in the heart, talking about venous return. Veins have valves, and that is one key component to improve venous return. Physical activity, muscles push the blood up the elevator, if you will. That is the deep vein in the leg, and that's how we get our blood from, fight gravity and bring our blood back to the heart. Large veins, medium veins, small veins, we call them venules. Blood flow, pressure, and resistance, okay? So the fact that we have large blood vessels, for instance, the abdominal aorta, and then we're going to have a medium-sized vessel, and then finally we're going to get it down to a smaller artery called an arteriole, and then a capillary level, there's a pressure backup. And that is one way, going from large to small, that we can create sufficient pressure to drive the circulation and service the entire anatomy. So if you can imagine like a 4 or 6 lane highway going down to 3 and then 2 and then 1 lane, that is going to create a steady pressure in order to facilitate flow. The cars have to get through that point, and there's quite a bit of effort that is being taken to eventually get the flow beyond that area. But the fact that we're going from large to small is one of the things that is going to help. That creates resistance and backs up pressure, allowing all these countless miles of blood vessels to plug into their anatomy. And so here we see that we've got we've got a system here, blood's coming in for this large cylinder, and then you see the 2 smaller cylinders to the right. That's going to increase pressure because there's a large volume of blood that has to be distributed, so it's going to increase the pressure in there. Now what happens if we can create a constriction after that? It's going to increase the pressure there in front of the constriction, and behind the constriction it's going to completely shut off flow. So there are ways that we can do this, and it is through the circulation, the circulatory system dilating and constricting. It's in large part due to the tunica media that is going to allow that to take place, okay? So there are ways that we can, via our homeostatic autonomic nervous system, that is going to be plugging into that tunica media, the muscular layer of those arteries and arterioles, that's how we're going to manipulate everything and make sure that the toes and the fingers and the nose and ears and everything throughout the body is going to get its fair share of nutrients and oxygen, etc. And there are feedback mechanisms that allow that to take place. Blood pressure is extremely important. That's why we have these values that allow us to determine, we have these mean values. So 120/80, why is it important that somebody is within that range? Or not 120/80 or 90/60. If you're within that range and your blood pressure is sufficient to send the blood where it needs to go. If you're above that area, well, maybe you've got too much pressure on the system, and that can create problems. And if you've got low blood pressure, are you going to be able to provide the nutrients? That's what we're worried about. Are we going to be able to service all this anatomy? We talked about the measuring of blood pressure. It's done with what's called a sphygmomanometer, or a sphig, and you auscultate the artery, you position the cuff, you're basically occluding the artery, and you're creating a backup in the pressure there. And there, as you let the pressure out, you can distinguish systolic from diastolic blood pressure readings and ultimately test the system. That's what it's all about. Hypertension is high blood pressure. Hypotension is low resting blood pressure. All right, so we can determine these by testing with our sphigs. Down below it says blood flow in arteries is pulsatile and also tends to rise with age. So, as we age, our entire AMP can go into decline just by a natural course of however many cellular divisions and the wear and tear of the pressure that is on these hoses going through the artery. Think about if you've got your garden hose on the side of your house or wherever you keep that right now. You store the garden hose, and I know some people take it in for the winter, but a lot of people leave it out there and just unplug it. If you go out next year, you're going to find that there will have been some changes in the flexibility of that hose, depending upon which type you buy and how quality it is. And so I know that the one that I have on the side is been out there for about 5 years, and it still works, but because of the position that I store it in, and it'll develop kinks, and the vessel wall will start to suffer, and it'll spring up leaks and stuff. So think about your anatomy and the forces that we're constantly dealing with in terms of pressure and nutrition and all of this over maybe 80 years of life. So if I use the analogy, or I told you a story about if we're doing cadaveric dissection and we feel the large arteries like an aorta, and you squeeze it between your thumb and forefinger, you can actually feel little crunchies in that. And this, what is supposed to be a flexible hose made of connective tissue and muscle, it's started to develop a rigid characteristic to it. And so what that is the natural aging process, and maybe some poor nutrition, and maybe some disease of the cardiovascular system, and maybe not enough exercise. But regardless of who you are, or how much exercise you do, you're going to develop some problems with your circulatory system with these hoses as the years progress. Not to say that you'll necessarily have a disease process as a result, a cardiac event, hopefully not, but blood pressure, take that to mean that the flexibility of the arteries will decrease over the years, just like the flexibility in all of our tissues will. And therefore, blood pressure values are going to be higher as we age. So you run across a senior citizen and their blood pressure is 140/90. Maybe that's normal for them. And there's not much we can do to really change that, influence it. Resistance, we talked about the analogy using a 6-lane highway going down to a 2 or 1-lane highway. That is going to create resistance. The fact that we have these large diameter vessels, and then all of a sudden we're down to the capillary level, creates a pressure, creates a backup, and drives a pressure that is going to feed the entire human anatomy. Also in play, blood viscosity. How thick is our blood? How hydrated are we? How long is the blood vessel we're talking about, and what is the radius? And here's a capillary with a bunch of red blood cells just stacked in there. We know that blood flows within plasma, the fluid component of blood, which the plasma is about 90% water. So that's our log flume right there. Vessel length, as the blood vessel increases in length, the resistance is going to decline. Just like if we stretched out a garden hose, and we had one that's, let's say our garden hose is 25 feet long, and then we got another one right next to it with the same supply, it's 50 foot long. What is the difference there? What is going to happen as a result? Which is going to have pressure, stronger pressure? Well, it's going to be the shorter one because it's closest to the supply. Also think about, I said, got the capillary refill test here. Think about how far the blood has to travel from the heart in order to get to your fingers and your toes. And then consider that some disease processes, for instance diabetes, they wreak havoc on the peripheral vasculature. So a lot of times people who have diabetes will have circulatory issues in their toes, for instance, poor circulation, because it's so far away from the heart. Blood vessel radius, we talked about the 6 lanes to 2. How do we regulate peripheral resistance? Well, there's local control. In other words, we can dilate and constrict the arteries. We also have nerves and hormones that exert an influence. They do so by, let's say, the nerves will be coming from the autonomic nervous system, sympathetic and parasympathetic, and they can influence, they can dilate or constrict the arteries. Also, hormones can do that as well. Remember, the neuroendocrine system controls everything. Here's an example of local control with dilation and constriction. I want to drop some knowledge on here about how do we increase vasculature. If, let's say, we were sedentary, we got on a health kick in a new year, and we would like to get in better shape. So we start exercising, we do it regularly, 3-4 times a week, cardiovascular fitness, at least an hour a day. The areas where the capillary beds were suffering and you didn't have sufficient blood flow, now they're going to increase. And so we call that neoangiogenesis. Yes, we can trigger growth of blood vessels into an area in response to the demands we place upon it. So we weren't exercising, now we are. Our muscles need more perfusion, they need more blood flow. And so we can actually grow new blood vessels. Pretty cool. Neural control. So the medulla, in the brainstem, the medulla oblongata and the pons, they're going to exert they're going to have these cardiac reflex centers in there. All right, so these little junctions that are going to help control the heart and the lungs and so many other automatic processes, subconscious processes. The vasomotor center in the medulla for heart and circulatory control. And we get feedback via this AMP called baroreflexes. Now, baro, the prefix there, baro means pressure. So there are certain blood vessels, like the carotid artery, has something called the carotid body. And that is going to, you can actually see it and feel it gross anatomically. It's a little bump on your carotid artery. And it's got these pressure sensors in there. So how much pressure is flowing through here? And it'll give feedback to where? To the medulla, to the brainstem. Chemoreflexes are these other functions of the circulatory system where there are structures in there that will test the blood, its chemical composition, how much oxygen, how much CO2, electrolytes, all that pH, all the content, the chemical composition of the blood flowing through a vessel. And finally, there's the medullary ischemic reflex. Ischemia means poor blood flow, like disease as a result of poor blood flow. So should there be sufficient blood flow, the brainstem will pick up on this and try to fix it. Here are examples of some hormones that influence the circulatory system. So angiotensin II and ANP, or atrial natriuretic factor. They can influence these hormones, these chemical messengers can influence the dilation and constriction of blood vessels. All right, so how do we redirect blood flow? Well, if we're sitting on our ass and not doing anything, we're going to have poor blood flow. So the pressure is not going to be feeding these particular areas. And we start going out and play tennis, and we train, we play, we get better and better. And our body becomes accustomed to this, and it becomes efficient at the heart and the lungs and the blood flow servicing areas such as the skeletal muscles, the quadriceps, the calves, the core muscles. So the physical exertion is going to increase perfusion to the lungs. That means more oxygen, oxygenation of tissues. The heart is going to get more blood and oxygen flow. The skeletal muscles are going to be empowered, going to be a lot of blood's going to be shunted to them so they can do their work. Also, the digestive system, the kidneys, the skin, they're going to receive less because they're not really a priority at that particular time. So think about what is the flow when you're sitting in class 6 to 8 hours a day to when you go home and you sleep for 6 to 8 hours. Or then you get up the following morning and you go play a tennis match. What is happening with blood flow? It's got to change. It's got to fluctuate based upon your activity, and it does that very well This is the basis for physical training and exercise. Poiseuille's law, it's basically the equation that explains the relationship between blood flow, how much is flowing, what is the pressure of the flow, how big are the blood vessels that the flow is going through, how long are the blood vessels, and viscosity. So it takes all these things into consideration, and it provides us some sense of what kind of blood flow we have into an area. It's not testable. Capillary exchange, okay, we talked previously about continuous capillaries, which are like straws, and then there are fenestrated capillaries, which are extremely important. These are like straws with little holes on them, in them. And so if a white blood cell senses that there's an infection nearby, it can come over and squeeze through the hole in the wall and go fight the infection. And if gases need to be exchanged, like oxygen and CO2, they can either jump in or out of the capillary through these fenestrations. So they're really, really important. And we're going to hear more about them as we move along. Transcytosis is when this red blood cell in the center of this capillary squeezes through the side of the little exit in the capillary, called a fenestration. Transcytosis. Cyto means cells, trans is meaning moving, so the cell is transitioning through these fenestrations of this, basically jumping out, getting off at an exit, and the red blood cell is going to, let's say there's a muscle cell nearby, it's going to go over there, it's going to drop off all of the nutrients and oxygen and all that good stuff, and it'll maybe load some waste products and stuff like that onto the red blood cell, and then it'll go back into the capillary. So pretty cool, right? And here we see a coronal section of a red blood cell, or a sagittal section, whatever you call it. And we could see the various endothelium, the squamous epithelium that has formed a tube, and you can imagine the different junctions between each of those cells and how they basically serve as the fenestrations. Filtration and absorption, well, just the take-home message that some things are coming in and some things are leaving. The fenestrations make it all possible. Did you know that the kidneys are essentially these they're full of these functional filtering cells called nephrons. And the nephron's job is to filter the blood. So there's a blood supply coming in via the renal artery. And the renal artery is coming straight off of the abdominal aorta. It feeds the kidneys with a certain blood pressure, and the blood pressure is going to drive filtration through these nephrons. The nephrons are full of these fenestrated capillaries, and the fenestrations allow us to service the blood or filter the blood and make sure we keep all the good stuff and get rid of all the bad stuff. Depending upon the blood flow, there can be variations in the level of filtration. Venous return is extremely important. We talked about the importance of deep leg veins and valves. So everything that is in pink here or red, those are the arterial system, and then the blue is the venous system. So when we get to the blue is all deoxygenated blood that's picked up waste products, and it's heading back to the heart to complete another circuit. It'll go to the lungs and be re-energized and filled up with oxyhemoglobin. And remember that all of our cells, regardless of the tissue type, they are constantly working very hard at the moment. And just like a car idling, the combustion that takes place, the work that those cells are doing, creates some waste products, and those waste products must be cleansed from our body. And so places like the liver and the kidneys make sure that happens, but the blood has to return to the heart, complete that circuit, otherwise we can undergo circulatory shock. So different mechanisms. Here we've got somebody doing a calf raise. We see the blood vessel, the vein in the middle. We know that gravity is constantly conspiring to take all of our fluids and all of our anatomy and stick it down to our feet. We're not going to let that happen because we're physically active, right? Then there's something called the thoracic pump. This is another method of venous return. Just by breathing properly, we're going to encourage a type of pumping action or a suction action that's going to take all of the deoxygenated blood and return it. The heart itself also is going to exert a force encouraging venous return. Skeletal muscles and our physical action encourages venous return. And then finally, gravity is going to help for everything that's above the heart. So draining the blood from your head, your arms, your shoulders, that's all going to help. Exercise is going to be crucial for venous return. I say it once, I say it 1,000 times. The heart rate is going to accommodate as we exercise. It's going to beat faster. It's going to create that suction. We're breathing efficiently, and the movement is life, and that's why it's important for us to exercise. Our blood is going to be completed. Our blood circuit is going to be completed, as opposed to somebody who's sedentary. If you just sit on your ass all the time, the blood is going to pool into your extremities, and it creates all kinds of problems because we're not getting the blood back to the heart efficiently. I told you a story about the drill instructor that was standing at attention for an hour or whatever, and he passed out because the blood was not making it back to the heart, and therefore not even, he wasn't moving. He was so still that the blood going to his brain stopped for a moment. Circulatory shock is a state that can occur when we don't have proper venous return. It can also happen due to insufficient blood volume, due to things like patient bleeding out, some sort of injury, internal bleeding, something like that. And it would be a bad thing. It would be a medical emergency. Different types, hypovolemic shock, so there's not enough blood volume. If there was an obstruction, that could cause a problem. And venous pooling, we just talked about that at length. Different types of shock. And that's the end of circulation. So we've covered blood, heart, and circulation. This is the cardiovascular system. This completes this all of your learning for this module. And we are going to have our exam this Thursday. I'll conduct a review. Come ready for it. 1, 2, 3, A&P.